Hey everyone, I wanted to make you a quick little review for the Unit 7 material prior to our test on Tuesday. So here we go. The general way we're going to do this, we're going to work our way through the learning objectives, and I'm going to highlight a couple of key things for each one, and then just a general reminder that there are attached to the event on Schoology some additional review problems. You can find those in the file called Unit 7 Review. There's no answers posted just yet, but they're there for practice if you'd like them prior to Tuesday's test. So here we go. So the first thing that's on our list is to identify matter. So classifying matter as either an element, compound, or mixture. So the piece to remember there is that when we think about matter, matter is just an umbrella term that can describe all kinds of things. And the fundamental subcategories that we talked about, one of them was pure substances. That's where you just have one type of thing. And then on the other side, where you have more than one pure substance, that's where you have something like a mixture. And we can break down pure substances further. If it's only made of one type of atom, that's called an element. And if it's more than one element chemically bonded together, and that's the key part there, chemically bonded together, then we call that a compound. And we know that within this realm of compounds, we have things such as ionic compounds, and we have covalent compounds. The key distinguisher between the two is that ionic compounds are held together due to electrostatic charges because they're ions. So that means that they involve electrons being transferred between those atoms when they form the compound. And in covalent compounds, they are held together by covalent bonds. Remember that covalent bonds are bonds that result from the sharing of one or more electrons between substances. Now, over here on the mixture side, we have a couple of different types of mixtures. If you have something where you cannot distinguish between the components, say something like salt water. Okay, salt water from the ocean, you can't really tell the salt from the water. So we call that a homogeneous mixture. When it looks uniform, it's homogeneous. Now, for something else, think like salad dressing, where you can distinguish the components, that's heterogeneous. Okay, so a heterogeneous mixture would be something like salad dressing, or you can imagine chocolate chip cookies. When we did the separating mixtures lab, the mixture we started with was a heterogeneous mixture because you could see the sand different from the iron, different from the salt that was there. So these are the different types of matter, and you should be able to look at something, in particular a chemical formula or a name, and be able to classify it specifically as either an element, a compound, or a mixture. And if it's a compound, you should be able to determine if it's ionic or covalent. And remember, the key way to know if it's an ionic compound is the vast majority of ionic compounds contain a metal and a nonmetal, whereas covalent compounds are made of only nonmetals. And the key giveaway for mixtures to determine if it's homogeneous or heterogeneous is if you can distinguish the components from one another. So if you can, then that's heterogeneous, and if you can't, that's homogeneous. Okay, so let's see how we're doing so far. So we've gone through that first bullet point, and next thing is going to be talking about how we can identify different ways to separate a mixture of two or more substances. And what I think would be helpful for that is I want you to think about the lab activity that we did where we actually separated mixtures. Now when we did that, you took advantage of the material's physical properties. Okay, so physical properties. Physical properties are things that describe a material that we can observe, and we can observe them without changing the identity of the substance. So examples of physical properties could be color. Jeez, oh Pete, I'm spelling horribly. Color. Other things like density, melting point, boiling point, those types of things. Just imagine anything that you can measure about a substance that doesn't change it, okay? Because even though we change the state of matter when we melt something, it doesn't change that substance from what it was originally. For example, a melted ice cube is still just water, even though we've melted it, okay? And the key distinguisher there is it doesn't change the identity of the substance. Where if we bring up what a chemical property is, chemical properties are things that describe the behavior of that particular type of matter that we can only observe through changing the material. So easy examples of that are going to be things like reactivity. Will it react chemically with something? Flammability. Will it burn? Okay? Those things you can't observe about the material without actually changing it. For example, you can't test that a match is flammable without actually changing the material substance and bonding within the match. You have to break bonds to actually be able to see that it's flammable. Okay? So key differences there. And we can use these differences in properties to separate them. For example, you use the fact that iron as an element is magnetic to be able to separate it from your mixture. And you used solubility. Okay? And solubility would be a physical property. And solubility just means does it dissolve in water or not. Okay? So you use that to separate the sand from the potassium chloride. Okay? And that's a physical property because you didn't change the identity of the potassium chloride when it dissolved in water. You just changed the state of matter that it was in. You made a mixture out of it. Okay? All right, so let's go back and see how we're doing. All right, so to identify, the ways we're going to separate a mixture of two or more substances is take into account their different physical properties. Next, the difference between covalent and ionic bonds. We already touched on that earlier, so that one's taken care of. Properties of ionic bonds. This is something we can talk about really quickly, so just listen carefully. Ionic compounds tend to have very high melting points, and they tend to be crystalline in nature, and they have very high boiling points as well. And that comes about as a result of the fact that they're composed of ions, and those ionic bonds that hold them together are very, very strong bonds. It takes a lot of energy to disrupt them. Okay? The other thing that's a key property of ionic compounds is they form conductive solutions when they're dissolved in water and when they're molten. So you have actually mobile ions that will allow charge to be carried through a solution. And that's something that's not true for covalent compounds. Covalent compounds have relatively low melting points. In fact, many covalent compounds are gases at room temperature, which means they have very low boiling points as well. Some of them do exist as solids at room temperature, but the vast majority of them will have a low melting point and low boiling point, especially in comparison to ionic compounds. And also remember that covalent compounds, even though some of them are soluble in water, think about sugar, that's an example, it doesn't make the water conductive when it's dissolved. So they do not form conductive solutions like ionic compounds do. Okay. This next bit on Lewis dot structures, we've already assessed on that, so I'm going to skip over that for this evening because it's not really our focus for the test that's coming up. Next, though, is a big one. This differentiate between atoms, monoatomic ions, and polyatomic ions. So, key thing to remember here, when we're talking about an atom is something that's going to have equal numbers of protons and electrons. Okay? An atom has equal numbers of protons and electrons. And you got to remember that that's completely different than ions. Ions have an imbalance. Okay? They have either more or less electrons than protons. And the key thing that we need to understand about ions is we have some species that we call monoatomic, and that just means they're composed of one atom that has an imbalance of electrons and protons, or we have an example of something called a polyatomic. And I'll just show you some examples here. So for monoatomic, that might be something like lead +1, or another one could be aluminum +3, or another common one, oxygen -2. Notice in all these examples, there's a single element involved, and there's an imbalance of charge. That's why it fits the bill as being an ion. And now's a good time also to remember that when we see something that has a positive charge, just remember that those things are called cations. And when you see something that has a negative charge, we call that an anion. Okay? Now if we go down and think about polyatomic, poly just means many. So a polyatomic ion is just an ion that's composed of more than one atom. So for example, some common ones that we've seen in class, ammonium is one. We also have seen nitrate quite a bit. And another one, carbonate, which has a -2 charge. And again, remember that whether we're talking about monoatomic or polyatomic, we can also be talking about things that are cations. In the example here, that's a cation, ammonium. Or we could be talking about anions, like these two examples here. So we can have monoatomic or polyatomic anions, and we can have monoatomic or polyatomic cations. Okay. I think that takes care of that one. Physical and chemical properties we went over already. Just take a look at your notes again. Just remember, physical properties are descriptors of matter that you can determine without changing the identity of the substance, whereas chemical properties, you cannot determine those properties without changing the substance. So things like flammability, reactivity, that type of thing. The next bit, understanding the role of energy in chemical reactions. Now, in this case, what we're going to be talking about is something called endothermic or exothermic. Okay? And those are words that we've introduced and used a while back in this course, but now we're looking at them specifically through the lens of chemical reactions. So for endothermic, just remember that that's a situation where you would have energy being put into a reaction. Okay, so energy is taken in or absorbed. So energy is absorbed by the reaction. And as a result of that, the surroundings, which is everything else, the surroundings become cooler. So if you were to do a reaction in a test tube and the test tube became cold, you would know that that was an endothermic process. It's the exact opposite case for exothermic. This is where you have a net release of energy, and energy is being released by the reaction. And that means that the surroundings become warmer. Okay, so that's endothermic and that's exothermic. You'll learn other ways to express those terms, not just through words, but also through some graphical means, but we're not going to worry about that for right now. Okay, that one's done. And we just did that as well. One thing I should mention, I just kind of overlooked this, the role of energy. Remember that when a chemical reaction happens, you always have to add energy to start the reaction, and we call that activation energy. But really that energy, the way we talked about it in class, was always the energy required to break bonds. And remember that in a true chemical reaction, you're always going to have two things. You have to break bonds, and then you have to make bonds, right? And energy is involved in both of those. In one case, it always takes energy to break bonds, and on the other hand, we always get energy released when new bonds are formed, okay? All right, moving on, and we're almost done with this. We've got right balanced chemical equations. So this is an important one, okay, because we haven't tested over this yet. So let's look at some examples of what we can do and what we can't do. So when you're given a chemical equation, it's important to remember that you cannot change subscripts. And remember, subscripts are going to be things like this 2 here and the 3 over here. Those are what we call subscripts. Those are fixed. You can't change those. But what we can add are things called coefficients, and coefficients always go in front of a chemical formula. So we can only add numbers where these little blue lines are. And the other thing we need to remember is this is all about the law of conservation of matter. So the way that we've done this in class is we start by listing the elements involved. And then we interpret the subscripts to tell us how many there are. So for example, on the reactant side, there are 2 nitrogen atoms and 2 hydrogens. On the right-hand side, on the product side, there's only one nitrogen and 3 hydrogens. So we have to come up with a way to make them balanced. So one thing I can do is I can put a coefficient of 2 in front of NH3. Now as soon as I make that change, I'm going to correct my count on this side. So now nitrogen has 2, and now for hydrogen there's 2 times 3. So that's 6. Now I notice that's balanced nitrogen, but hydrogen is still unbalanced. So I have to go back and add a coefficient on the reactant side to balance that out. And so I know that there's already a subscript of 2, so I'm going to use a coefficient of 3 because 3 times 2 will give me the 6 that I need. So this is an example of a balanced equation, and just remember the only thing you can change are coefficients. Okay? And one other thing that might be helpful at this point is when you count atoms. And let's look at something like, this was a compound we had used in class as a demonstration, but it's a good one to look at to make sure we understand how many atoms of each element are there. So we've got nitrogen, hydrogen, chromium, and oxygen. So if we wanted to count how many atoms there were, this 2 applies to everything in the parentheses. So there would be 2 nitrogen. And we have to remember that it's distributive as well, so we have to multiply. So 2 times 4 to give us hydrogen, that gives us 8. 2 chromiums, and then 7 oxygens. So remember in particular, when you're dealing with substances that have a polyatomic ion or some other subcompound within parentheses, remember that the subscript outside of that polyatomic ion always multiplies by whatever the formula of the polyatomic ion is. You should be in good shape. Okay. Next is going to be looking at types of reactions. And there were 5 types, and let's go over them relatively quickly. So we've got one type, synthesis, our second type, decomposition, and then we have single replacement, double replacement, and combustion. The general format for these, in terms of like a general equation, for synthesis, it's always 2 things coming together to form one larger thing. For decomposition, it's the exact opposite. You're taking something that's rather complicated and breaking it down into 2 or more simpler things. For single replacement, it's where you have one particular element reacting with a compound, and that element kicks out the similar element. So if it's a metal, it'll kick out the other metal. If it's a nonmetal, it would kick out the other nonmetal. In this case, the way I've drawn it is for a metal. So A kicks out B and replaces it into the compound. Notice the pattern. Element plus compound gives you element plus compound. Now for double replacement, it's similar, except involving 2 compounds. So the compounds swap cations effectively. And the products will be CB and AD. And understand the order that I've drawn these. As long as they're on the product side, it doesn't really matter. Okay, I could have done AD plus CB. Makes no difference. And finally, combustion. And we limited our discussion of combustion to hydrocarbons. So hydrocarbons have carbon and hydrogen in some formula. So the X and Y, it'll depend on the hydrocarbon. But when you burn something, when you combust it, you're combining it with oxygen. And when you burn a hydrocarbon, the vast majority of the time you get carbon dioxide and water. So the dead giveaways for a combustion reaction is you should see oxygen as a reactant, and then CO2 and H2O as products. And you've got a nice sheet that we went through in class that had you practice this, so hopefully this won't be too much trouble for you. I think we've got one last thing to really talk about, and then we'll be done for the evening, and that's naming compounds. And at this point, we've practiced a lot of naming, but let me make sure that I go over a couple of helpful hints with you. Remember that when you're naming compounds, fundamentally, you're going to break it down into either an ionic compound or a covalent compound. Now, we've done a lot of these at this point. So key things that you should remember: covalent compounds utilize prefixes. And those prefixes, we use them to indicate amount. Of a particular atom within the compound. Whereas with ionic compounds, we don't use that. In fact, the ionic nomenclature system that we use is effectively, you take the cation name and you add to that the anion name, which if it's a binary compound, it's going to always end in IDE. And if it's a polyatomic, you just take the name of the polyatomic. The key thing to remember here is that you've got to watch out for a couple of things. Primarily, you have to be able to identify for ionic compounds when you're dealing with polyatomics and when you're dealing with metals that may have more than one oxidation state. And a primary example of that would be something like this. If we look at both of these compounds, they contain the exact same elements, and they're both ionic. We know that because iron's a metal, oxygen's a nonmetal. And the way we would go about naming them might just be the name of the cation, iron, and the name of the anion, which is not oxygen. Remember, the anion's name gets changed to oxide. Now, if we look at this, we would come up very quickly with the name that both of them were iron oxide. That can't be right because there's definitely a difference between them in terms of their formula. So we have to show that as well. And so the way we do that is by showing a Roman numeral. Now, figuring out the Roman numeral takes a little bit of thinking and reverse engineering. So we have to remember that if the iron is the piece of the puzzle that we're not certain about, well, the oxygen should be known. The oxide ion, we know its oxidation state. It's a -2. So if oxygen's a -2, in this first example, iron must be equal but opposite, because ionic compounds always come together in a ratio such that their net overall charge is 0. So that means iron has to be +2. So the name becomes iron, Roman numeral 2, oxide. Now in this case, we've got 3 oxygens, which gives us a total charge of -6, which means the iron has to balance it out as a +6. But there's 2 of them, so each iron shares that charge equally, and so this is iron, Roman numeral 3, oxide. This is the thing that I see most students make mistakes with, that you get the name iron oxide right, but then you forget to put the Roman numeral in parentheses there. As far as covalent compounds go, you guys haven't made a whole lot of mistakes with those. Just remember that you'll have your prefixes available to you, and look at the examples that we've gone over in class. So, I think that is it. That's everything that's on our list here. And also remember that there's practice problems in the review for you to try. So please feel free and try them. Hopefully you found this video helpful. You guys have a great evening. Good night.